All right, gang, here we go. So this is Chem 1, Unit 5, Part 7. We're talking about empirical and molecular formulas. Now, this is probably the hardest section in the whole chapter, if I had to label one. So make sure you do lots and lots of practice problems. Make sure you do. Pay attention. You might have to watch this video more than once, but don't be afraid to ask questions. All right. So we're talking about empirical molecular formulas. First of all, let's start with empirical formulas. So if we have this compound NH4NO2, okay, this, remember, we've talked about before how this represents the number and type of elements that are in that compound, right? So in this particular one, we've got two nitrogens, right? One there and one there, four hydrogens and two oxygens, and that's what these balls represent here. The gold ones are the nitrogens, the blue ones are the hydrogens, and the red one are oxygens. So this is what the actual formula looks like for, this would be ammonium nitrite. Okay, but the empirical formula for this, well, the empirical formula is this guy over here. Now notice that it's essentially the same thing, only we've divided all of the elements by 2. Okay, and the reason we do that is because it's a representation of the smallest whole number ratio of elements. Okay, so the empirical formula is the smallest, okay, whole number ratio of elements that are in your compound. All right. Okay. So the actual formula is what actually contains, and the empirical formula is the smallest whole number ratio. Now the reason that we even care about this is there's a couple of reasons, but the main reason is that there's a machine called a mass spectrometer, and we talked about this really briefly when we talked about finding the isotopes of a compound. And what a mass spec will shoot out, you give it a sample, and based on how it uses magnets to spin your elements through a tube, it'll actually tell you the percentage of how much of each compound you have inside your compound. All right, and so that's the kind of idea. And then you can use that percentage information to figure out the empirical formula. And so that's really the main reason we care about empirical formulas, is because it's really easy to find the percentage of each element, and then we can find the smallest whole number ratio. Then we can use additional information to find the molecular formula, or the actual formula. All right, in this space filling model, you don't really need to know anything about this more than just the fact that this is kind of what it actually looks like, right? You've got your ammonium here, your NH4, right, N, and then your 4 hydrogens surrounding it, and then your NO2. But we're really not spending time on space filling models here. Okay, so an empirical formula consists of the symbols for the elements combined in a compound. The subscripts show the smallest whole number ratio, okay, of the different atoms in the compound. So empirical formula, smallest whole number ratio. Okay, in an ionic compound, the formula unit, okay, so remember the formula unit, this is how we represent an ionic compound, is usually the compound's empirical formula. So essentially with most ionic compounds, just whatever your empirical formula is also what your formula unit is. However, for molecular compounds, the empirical formula does not necessarily indicate, okay? In fact, most times the molecular compounds, the empirical formula doesn't actually show you what's actually in it. An example of this is if you have diborane here. Okay, the empirical formula for diborane is BH3. However, you should recognize that this di out front means that there should be 2 borons, right? 2 borons, but BH3 only has 1. The reason it's called diborane is because the actual formula, or the molecular formula, is this guy here, B2H6, and there's your diborane because you got 2 of those guys there. But the empirical formula is BH3. So a lot of times in molecular compounds, your empirical formula only shows you the smallest whole number ratio. It doesn't actually show you what your molecules actually, how many of each element you actually have in your compound. So, so this is the poem we use to calculate the empirical formula. Okay. So this is an important poem. This is on the back of the periodic table you have as well, but it's very useful. So we go percent to mass to mole, divide by small, multiply to the whole. Okay, so if you're given percentages, you convert them to their masses. Okay, and I'll show you the trick on how to do that. All right. Once you have the masses, you need to convert that to moles. That means you need to use the molar mass. Remember all that stuff from before? Pretty exciting. Okay, so this is a couple of units old, so you might have to dust off some of that part of your brain. Then you're going to divide by the smallest mole out of the ones you calculated, and you're going to multiply to the whole numbers. And we'll do a couple of practice problems here. All right, so diborane. Well, we already looked at this, and we know diborane, the empirical formula, should be BH3. So this kind of gives us a place to shoot for, making sure we got it. All right, so it says the percentage composition is 78.1% boron and 21.9% hydrogen. Calculate the empirical formula. Now these percentages, these are percentages by mass. Okay, so by mass, it's 78.1% boron and 21.9% hydrogen. All right, so the first step is mass to mole. Well, if we assume that we have 100 grams of substance, then that really means that we can assume that these guys, we have 78.1 grams of boron and 21.9 grams of hydrogen. So that first step, percent to mass, is really easy. You just rewrite your percentages, and instead of writing percent, you write grams. So we'll just go 78.1 grams of boron, okay, and 21.9 grams of hydrogen. Easy peasy. All right, so that was percent to mass. Now we go mass to mole. Okay, so now we got to divide these guys and get them to moles. So we'll put grams of boron in the bottom here, moles of boron in the top. Okay, remember we always put 1 with moles. And the mass of boron, well, we find the boron on the periodic table, and it's right above aluminum, and its molar mass is 10.81. All right, so 10.81. All right, and we're going to multiply. We're just going to divide that. So we'll take 78.1 divided by 10.81, and we get 7.22. Now, on these, I wouldn't round, or don't round until you get to like 4 or 5 decimal places. So I'm going to say 7.2248. Okay, all right, and the reason you do that is because of the next step. All right, because we need to have this as non-rounded as possible. All right, so 7.2248. Now we're going to do the same thing with our hydrogens. All right, so we put for every 1 mole of hydrogen, we have 1.01 grams of hydrogen. All right, so the grams go on the bottom because the grams are here and we need them to cancel. All right, so we'll take 21.9 divided by 1.01, and we get 21.6832 moles of hydrogen. All right. So now we're going to, and so that was our mass to moles, right? We did percent to mass, mass to moles. That's where we're at. Now we're going to divide by small. So pick the number of moles that's the smallest and divide both of them by that. Well, 7.2248 is smaller than 21.6832. So we're going to divide them both by 7.2248. Right, divide that by 7.2248. All right. So we divide those. We know that's going to give us 1. And if we divide those, 7.2248, we get 3.00. All right. Now the next step tells us to multiply to the whole. So essentially what you want to do is, if these numbers are not whole numbers, you're going to multiply them by a whole number until you get whole numbers. But 1 and 3 are both whole numbers, so these numbers here, we don't have to multiply by whole because they're already whole numbers. These numbers are the subscripts, okay, of your formula. So this says we have 1 boron, right, because we started with borons over here. So our empirical formula is B1, but we don't write the 1s, remember that. And then that 3 says we have 3 H's, so it would be BH3. So that's our empirical formula for boron, or diborane, excuse me. All right, let's do another one. It says quantitative analysis shows that a compound contains 32.38% sodium, 22.65% sulfur, and 44.99% oxygen. Find the empirical formula. All right, percent to mass. So we're just going to write 32.38 grams of sodium. All right, remember for percent to mass, we just take out the percentages and write grams instead. 22.65 grams of sulfur and 44.99 grams of oxygen. All right, so that's percent to mass. Now mass to moles. All right, so we're going to convert all of these guys to their respective moles. All right, so for every 1 mole of sodium, we have 22.99 grams of sodium. For every 1 mole of sulfur, we have 32.07 grams of sulfur, and for every 1 mole of oxygen, we have 16.00 grams of oxygen. All right, so solve all that, guys. So we take 32.38 divided by 22.99. We get 1.408. 1.408. We'll say 4 moles of sodium. 22.65 divided by 32.07. Get 0.7063 moles of sulfur. And 44.99 divided by 16, we get 2.81. 19 moles of oxygen. All right, now, so that was per mass to moles. Now we'll divide by small. 0.7063 is the smallest one, so we'll divide that one by 0.7063. We'll divide this one by 0.7063, and we'll divide this one by 0.7063. So this is going to be 1, obviously, because it's just divided by itself. The bottom one I already have in my calculator, so I'll just do that one first. 0.7063. We get 3.98. Now this is close enough to round to 4, so we're just going to say that's 4. All right, and then 1.4084 divided by 0.7063. Well, that should be 1.99. So that's going to be 1.99. That's close enough to round to 2. So what this is saying is we've got 2 sodiums, Na2, 1 sulfur, and 4 oxygens. All right, and you should recognize this. This guy is sodium sulfate. Pretty slick. All right, so there's your empirical formula for sodium sulfate. All right, now molecular formula, this is where life gets more exciting. So remember, empirical formula just told you the smallest whole number ratio. Your molecular formula is what it's going to actually tell you what the actual compound has in it. So it's going to tell you the actual formula of the molecular compound. All right, so remember, the empirical formula may be the actual molecular formula. They could be the same thing, but a lot of times, especially with molecular compounds, they're not the same. So in order to compare these two things, we're going to use this new thing called the formula mass, okay? And so we're going to talk about, we're going to have to calculate the formula mass first, and then we're going to use this formula mass and this ratio to find this x value. So what this is saying is the empirical formula mass should be some value that's a ratio, a whole number ratio of the molecular formula, all right? So here we go. So the empirical formula of a compound of phosphorus and oxygen was found to be this, P2O5. So there's your empirical formula. All right, it says experimentation shows that the molar mass of this compound is 283.89. What's the compound's molecular formula? All right, so first, so remember here, we've got, so it tells us what the molecular formula mass is, right? It says right here, or molecular formula mass and molar mass are the same thing, all right? And it tells us it's 283.89. All right, so that's this side of the equation. Now we need, and we want to find x, so that means we need to calculate the empirical formula mass. Well, in order to do that, we have to use the periodic table and our empirical formula. So what this is saying is P2O5, okay, this has 2 phosphoruses and 5 oxygens. All right, now this, and then we're going to look at the periodic table, and we're going to add up all of these elements' formula mass, or molecular masses, all together. So we've got 2 phosphorus, and phosphorus has a molecular mass of 30.974. So we'll say 30.97. Okay, and then we have 5 oxygens, so 5 times 16.00. All right, now we're going to add all those guys up together. So 2 times 30.97 plus 5 times 16. So that's going to be 141.94. So that is the empirical formula mass for our thing, because we've had the empirical formula and we figure out the total mass just by adding up all the elements that are in it. 141.94 grams per mole. All right, so we'll just put grams per mole here. All right, now what we need to do is we'll take this number and divide it into the 283.89. Okay, because we know some number times our 141.94. 141.94 should be equal to 283.89. So to solve for x, we'll just divide that over. So x is equal to 283.89 divided by 141.94. So we'll take our 283.89, no. Why are you guys letting me screw this up? 283.89, there we go. 89 divided by 141.94, and we get 2 0.0000, whatever. All right, so that means our x value is 2. So that means there's 2 sets of these empirical formulas, okay, inside each of our molecular formulas. So that 2 simply tells us we need to multiply all these subscripts by 2. So we're going to multiply the P2 by 2. So we're going to have P4 because 2 times 2 is 4. And then we'll have 5 times 2, which is 10. And so this guy here, that's the molecular formula. All right, so just to recap what we've done here is we had the empirical formula and we needed to figure out what the molecular formula was. Well, we know that the molecular formula mass is this 283.89, so we had to find out the empirical formula. So we found out that the empirical formula was 141.94, and then we divided that into our 283.89, and that ratio told us how many empirical formulas there are inside of each molecular formula. So there's 2 empirical formulas inside each of the molecular formulas, so we just multiplied our empirical formula by 2. All right, this number here that you get when you divide these should always be really, really close to a whole number. If it's not, that means your empirical formula is not quite right. Now, in this particular case, I just gave you the empirical formula, so it's not such a big deal. But in other problems, we could start with one like this, where you find the empirical formula, and then from whatever you get there, you figure out the molecular formula. So anyway, so do lots and lots of practice problems. There's lots of practice in your packet, and then let me know if you have any questions. Good luck.